welcome to this fourth and final lecture on the theory of time. In lecture 3, we talked about Albert Einstein and his theory of relativity, and in particular his assumption of the principle of invariant light speed. And we disagreed that that was a valid assumption. We know that experiments within the local at-rest inertial frame of reference does prove that light travels at speed c. However, this is not the issue. The issue is, how does light travel between inertial frames of reference? And it is there that we say that the speed of light is not constant. And in fact, we use the analysis of stars in distant galaxies that was performed by Vera Rubin, where she tried to measure the orbital velocities of stars within galaxies and found that she could not measure a difference in the orbital velocities. And we said that that was proof that the principle of invariant light speed was incorrect. That the correct assumption is the principle of non-constant light speed. Well, in this lecture, we're going to continue to challenge the ideas of modern physics. First of all, we're going to complete the transition from the galactocentric universe to the modern concept of the Big Bang Theory. We'll talk about the geometry of the universe as scientists view it. We will then start challenging that idea. We'll challenge Hubble's law. We'll look at some of the data coming from spacecraft that NASA has launched that seem to cast doubt on the present geometry, or the thought of the present geometry. And then we're going to create a new geometry based upon those observations. In developing that new geometry, we're going to find that we have to add a new spatial-time dimension. And we'll talk about that as we get into it. We'll show that by adding this additional dimension, that ideas of scientists that seem illogical now will suddenly start making a lot more logical sense. Finally, we will take a little bit of time to talk about just what is the constant c. Now, we left off with the galactocentric universe, and William Herschel had developed this idea back in the 1700s that our sun was but one sun in this Milky Way galaxy that consisted of the entire universe. And our sun orbited around the center of the Milky Way galaxy. But Herschel, when he viewed our universe through his telescope at the time, yes, he did see points of light, but he also saw some very fuzzy objects, nebulous objects, and he called them nebulae. And it's going to be those nebulae which is going to lead us to the next version of the universe. Now, what we needed to get to the next version was a bigger telescope. And what they did was they built a bigger telescope on Mount Wilson in the area north of Pasadena, California. And they created what was called the Hooker telescope. And this Hooker telescope had a 100-inch mirror at the base of it. Now, the bigger the mirror, the more light that can be collected and focused on the eyepiece. And this 100-inch Hooker telescope became the largest telescope in the world at the time. Now, the person lucky enough to get to use this telescope was an American astronomer named Edwin Hubble. In the 1920s, Hubble pointed that Hooker telescope at the Andromeda Nebulae. He had a much clearer image and said that this thing looks like another galaxy. Herschel said there was only one galaxy, but all of these fuzzy nebula appeared to be additional galaxies. And the question was, were those things, those objects within our Milky Way galaxy, or were they separate from them? To accomplish this, he needed a way of telling distances in space. Now, this technique was developed by a woman astronomer named Henrietta Swan Leavitt, and it was a procedure called standard candles. And what she did was that she had observed Cepheid variable stars. Now, what's a Cepheid variable star? Well, it's a star that pulsates. And what Henrietta Leavitt found was that some of these Cepheid variable stars pulsate slowly, and some pulsate fast. But when you have two Cepheid variable stars that pulsate at about the same rate, that the luminosity of those stars were the same. Now, Hubble could use this idea to measure distances in space. So he could look at a Cepheid variable star in the Andromeda Nebula, determine its pulse rate, from that get a figure from Henrietta Leavitt's formulas as to what the original luminosity of that star was. He also had the luminosity of the star as it appeared through the Hooker telescope. And scientists know that the luminosity decreases with the inverse square of the distance between where the object is and where it's observed. And so Hubble was able to use this fact to calculate a distance to the Andromeda galaxy. Now, he looked at Cepheid variable stars within the Milky Way galaxy and came up with distances under 100,000 light years distance. But when he looked at the Cepheid variable stars in the Andromeda galaxy, he came up with a distance of 2.5 million light years. Well, this was the evidence he was looking for to say our universe consists of multiple galaxies. The Andromeda galaxy was well outside of our Milky Way galaxy, and all the different nebula that he looked at turned out to be other galaxies that were outside of our Milky Way galaxy. So we've made the shift away from the galactocentric universe to a universe that has many galaxies within it. The next thing that Hubble did was there was another astronomer that was working out of the Lowell Observatory outside Flagstaff, Arizona. His name was Vesto Slipher. And what he was doing is he was doing redshift analysis of these same nebula that Hubble was working on. And so Hubble combined his research with that of Vesto Slipher and created a graph that you see on the screen that is called Hubble's law. The horizontal axis uses the standard candles that Hubble used. The vertical axis used the redshift and is marked recessional velocity. Remember at this time that it was felt that redshift measured recessional velocity. And what this graph shows is that there is a very strong correlation between this standard candle measurement and the recessional velocity. These galaxies lined up almost directly on the line of correlation. Some were slightly above or slightly below, but for the most part, they lined up very well. It was a very strong correlation. And so what Hubble's law tells us is that the farther an object is from us on Earth, the higher is its recessional velocity. And so essentially what we're getting are two values for one observation. Whether we look at standard candles or redshift, we will get both a distance and a recessional velocity. Now, at the same time, there was a Catholic priest. His name was Monsignor Georges Lemaitre. And he actually derived Hubble's law theoretically using Einstein's general relativity equations. But Lemaitre went one step further. He said, if these galaxies are having a recessive velocity away from Earth, can I extrapolate backwards in time to see if there was a point when all of these galaxies were right on top of each other. And his calculations showed that yes, indeed, at 13.8 billion years ago, all of these galaxies would have been on top of each other. And Lemaitre interpreted this as 13.8 years ago was the start of our universe. Now this was a totally new concept, that our universe could have a beginning to it. And what happened is that it was like there was a big explosion, and from this one point, the universe exploded outwards and is still expanding outwards today at an ever faster rate. And that became the concept of the Big Bang theory today. That we started out as an individual, either singularity or small section of space, that all the matter was there, and that over the last 13.8 billion years ago, all of this matter has been flung out to create our current universe. Okay, so can we create a geometry off of this? What do we have to work with? Well, we got the ideas of Einstein, who says that the universe is non-Euclidean. We've got the work of Lemaitre that says the universe is expanding. We've got Hubble's law that says the farther something is away from us, the faster it is moving away from us. And one other important point is the general belief that you cannot point at a location in the sky and say that is where the Big Bang occurred. You just can't do it. So we need some kind of a geometry that satisfies these conditions. And the typical example that scientists use to illustrate this geometry is a balloon. So according to Lemaitre, at the beginning, all the matter in the universe was tied up into a very small area of space, if not a singularity. Then it exploded outwards, and we can simulate that exploding outward by inflating the balloon. Now Einstein says we have a non-Euclidean geometry to space. Well, the geometry of space is not the balloon and everything inside of it. It is only the surface of the balloon. The surface of this balloon is a non-Euclidean geometry. The space inside of the balloon is not part of our universe. The space outside the balloon is not part of the universe. So now we've got the idea of a non-Euclidean universe going here with this example. Now I've also put 3 dots here, and we're going to try to test Hubble's law with this example. Right now these dots are about an inch apart. If we were to continue the expansion of our universe, now when we look at these 3 dots, they're about 2 inches apart. And so what we're saying is that if we are an observer on one of these dots, that the other 2 dots, as we go farther in distance, they are traveling faster away from us. That's that recessional velocity. The farther something is from us, the faster is its recessional velocity. So this balloon is illustrating Hubble's law. Now the final question that we had was, well, where is the Big Bang? Well, where was the Big Bang for this balloon? It was this crumpled up balloon inside, somewhere in the center of this balloon. But recall that the inside of this balloon is not part of our universe. Neither is the outside. And so some people will say that we cannot point to a location in the sky and say that is the Big Bang, because the point of the Big Bang is not within our universe. Now, there's a second interpretation that people put on this, and they say that what was the Big Bang is now the surface of this balloon. that the universe is just getting bigger. That Big Bang is just getting bigger. And so, where is the Big Bang? Well, it's in this podium, tables, chairs, cities, the planet Earth, the solar system. Everything around us is the current form of the Big Bang. So the Big Bang is in our universe, in everything in our universe. So that is the geometry that scientists tell us is the geometry of our universe. Now, there are people that question this. They think this is a rather odd geometry. And in fact, the theory of time is going to question this geometry. And so we're going to kind of toss out this geometry and go to look at what is wrong with the basic assumptions that went into that geometry. Well, first is Hubble's law. Remember that vertical axis in Hubble's law that measured recessional velocity? Well, recall that according to the theory of time, you cannot measure the recessional velocity using redshift analysis. So under the theory of time, that vertical axis can only be labeled redshift. Now, we haven't talked about yet what redshift does represent. So we're going to take a few minutes now to describe that. Redshift under the theory of time is entropy, for the most part. What is entropy? Entropy is something that goes in one direction only, from an ordered state to a disordered state. We can think of a cup of piping hot coffee sitting on a counter. Well, what's going to happen to that coffee? Spontaneously over time, it's going to cool down until it reaches equilibrium with the temperature of the rest of the room. It will not spontaneously heat up on its own. It will take the infusion of additional energy to heat that cup of coffee back up. But cooling down happens spontaneously. Now, another example of it is pouring cream into that cup of hot coffee. What happens? The cream distributes itself throughout the coffee, and the coffee turns a brownish color. That's a one-way action. There is no way that a brownish cup of coffee is suddenly going to divide itself into a white cream and a black coffee. That just can't happen. Now, in thermodynamics, we talk about the ability to perform work, or useful energy that can perform work. And so entropy in this context is a decrease in usable energy that can perform work. And this is what we say happens to photons. That photons traveling through empty space will gradually lose usable energy. Well, what is usable energy for a photon? Well, that is the frequency of the photon. So what we're saying is that once a photon leaves its source, some star, it will have a high frequency with a short wavelength, but the longer it travels through empty space, that frequency will gradually slow down, and the wavelengths will gradually get longer. And we can measure this in terms of temperature, in particular the Kelvin scale. Now, the Kelvin scale is like Celsius in that, except that the 0 point is moved to a location of absolute zero. You cannot have a negative temperature on the Kelvin scale. Now, do we have any examples of photons cooling down over time? And the answer is yes. It's in the cosmic microwave background. Cosmologists think that the cosmic microwave background was created at a point 400,000 years after the Big Bang. And at that time, the temperature of the cosmic microwave background was estimated to be around 3,000 degrees Kelvin. we have launched space probes that measure the current temperature of the cosmic microwave background. And the current temperature is 2.725 degrees Kelvin. It's just below 3 degrees Kelvin, just above absolute zero. So what we're saying is that in the 13.8 billion years that those photons in the cosmic microwave background have been moving through the universe, that they have cooled from 3,000 degrees Kelvin down to only 3 degrees Kelvin. Now, this is one of those areas where scientists start making up stuff to try to explain this decrease in temperature. And what they say is, well, because the universe is expanding, we've got new space being created, and this new space is stretching the waves of the photons so that they are stretching out, getting longer wavelengths, and hence shorter frequency or smaller frequency. Well, a big problem with that idea is that there is absolutely no evidence that that's occurring. And in particular within galaxies. There's no evidence within galaxies of any type of new space suddenly appearing. But the theory of time, with this concept of entropy, has a very valid, scientifically proven explanation for why that cosmic microwave background has cooled over the last 13.8 billion years ago. Now, back to Hubble's law. What we're saying is that the distance from the horizontal line up to that diagonal line of correlation, that distance represents entropy. As entropy gets higher, frequency gets lower and temperature gets lower, and hence redshift gets longer. And what Hubble's law should read under the theory of time is that the farther a star is from the Earth, the more time that photon is traveling through the universe, the more time it has to cool down, causing a higher redshift value. So entropy is the primary reason for the redshift that is observed in Hubble's law. Now there is a secondary reason for the redshift, and that is that as the photons move through interstellar space, they are affected by the gravitational forces, and they can speed up and slow down. That also affects redshift. And so that becomes a reason why you see some of the galaxies above or below the line of correlation. But in general, the line of correlation represents entropy. So let's look at some of the other issues that have come up recently. NASA has put up what's called the Hubble Space Telescope. You've probably seen pictures of it. Well, in 1995, the Hubble Space Telescope was conducting something called the Deep Field Studies. And what they did was they pointed the telescope at different directions in the celestial sky. One point in the northern hemisphere in the constellation Ursa Major, another one in the southern hemisphere in the constellation Tuscana. And they picked a particular point in the sky because previous observations had indicated that nothing was there, that it was just completely black. So what they did is they would point the telescope at that point in the sky, they would open the shutter and leave it open for like 30 to 40 hours to see how much light comes in and what it produces. Well, the images that came back in both of those directions is similar to what we see on the screen now. We see a multitude of very old galaxies. These types of galaxies are called globular clusters, and they indicate galaxies that are 10 to 13 billion years old. Okay, so we need to understand a little something about the timeline of the Big Bang. From the point of the Big Bang out to that point 400,000 years ago when the cosmic microwave background was created, our universe consisted basically of plasma. And it was very foggy, and you really can't see through it. But once the nuclei captured electrons, the skies cleared, and that allowed the photons to go out as the cosmic microwave background. So at that point, we had just individual atoms, primarily hydrogen atoms with a few helium atoms mixed in. And we had a period called the Dark Ages where everything was just dark. There was no light whatsoever. But over time, those hydrogen atoms were kind of pulled together by gravity and started clumping together. And if you clump it and give enough pressure to those hydrogen atoms, all of a sudden a star is going to form. And so these became the first stars. So now the universe has just individual stars out in it. But over time, those stars start getting pulled together by gravity, and they start congregating together to form these globular clusters. And those became the earliest galaxies to be created. And those globular clusters are what we're seeing in these deep field studies of the Hubble Space Telescope. So what we're saying is that even though that point in the sky looks black, that you look long enough with a big enough telescope, you're going to be looking way back 10 to 13 billion years ago. And if you put a bigger telescope out there, like the upcoming James Webb Space Telescope, you're going to be able to see back to those first stars that were created. And if you build an even bigger telescope, you will get back to those dark ages. And a bigger telescope will get you back to the cosmic microwave background. And beyond that is the Big Bang. And so the conclusion from these deep field studies is that the Big Bang is actually within our universe. It's not the podium and table and chairs and stuff around us, but it is something within our universe. However, it is in every direction we look in the sky. So no matter where we point, scientists know that when we go look deeper in whatever direction we point in the sky, we're going to see those globular clusters. And going deeper, we'll see the first stars. Deeper, we'll see the dark ages, and then that foggy time before the cosmic microwave background. And if we could go farther, we would be at the Big Bang. Okay, so that's what the Hubble Deep Space Study or Deep Field Studies tell us. It exists, the Big Bang exists within our universe in every direction. Well, there is another type of space probe out there that gave us some additional information about our universe. And the first one was the Wilkinson Microwave Anisotropic Probe, or what we call WOMAP. And this was launched by NASA in June 2001. And the purpose of this, or at least one of the purposes of this probe, was to try to determine the geometry of the universe. Well, how do you determine the geometry of anything? Well, back in high school geometry, we learned about Euclidean geometry. Euclidean geometry is considered a flat geometry. And if we have a non-Euclidean geometry that curves in on itself, then triangles are going to be different. We learned in geometry class that there was a theorem that says the sum of the angles of all triangles is going to be 180 degrees. Now, if you've got this non-Euclidean sphere, then the sum of the angles of any triangle on that sphere will actually be more than 180 degrees. If you have a non-Euclidean geometry that moves outward, then the sum of the angles of those triangles will be less than 180 degrees. And so what the world map probe did was, it used itself as one point, and it looked at two different points in the cosmic microwave background to create triangles. And it tried to measure the sum of the triangles, or sum of the angles. In 2012, NASA released the data from the WOMAP probe, and it showed that the curvature of the universe was less than 0.4% of flat. That's well within the margin of error to mean that our universe follows the plain and simple Euclidean geometry, that same geometry that we learned back in high school. Now, the European Space Agency, they had their own probe that they launched, and between 2009 and 2013, it was doing things similar to the WOMAP. And it also concluded that the geometry of our universe is Euclidean. So, Einstein is wrong in his thoughts that our universe was non-Euclidean. We've got space probes now that are saying our universe is Euclidean. All right, well, let's suppose that we're dealing with a Euclidean geometry and we've got our three-dimensional universe here. And so we've got the Big Bang. It's exploding outwards. Now, this is almost like the balloon example, except that now space includes the stuff inside of that shape. We can put the origin of the universe, or the origin of that Euclidean geometry, at the point of the Big Bang and measure that expansion rate out on the three axes. Now, someplace out there is going to be the Earth. Pick one. Right there. That's the Earth. Where's the Big Bang? It's down here at the origin. In this three-dimensional Euclidean model, what we're saying is that we on Earth should be able to look in one direction and see where the Big Bang occurred. Not in every direction, but just in one direction. So, according to the Hubble Space Telescope, we've got something wrong with this geometry. Our space cannot, or our universe cannot be a three-dimensional Euclidean geometry. However, it can be a four-dimensional Euclidean geometry. Scientists have known for a long time that when you look out into space, that you are looking backwards in time. So when Hubble looked at the Andromeda galaxy, 2.5 million light years away, he was looking at a galaxy as it existed 2.5 million years ago. There is an association when you look out in space between distance and time. For every light year distance, you've got a year of time that you're looking. And this continues back all the way to that 13.8 billion years ago. All right, so what this capability means is that we've got a spatial time dimension out there that equates distance with time. All right, so what then is the geometry of the universe? Well, according to the theory of time, the Big Bang occurred at a certain point that we'll still call the origin, but now of four-dimensional space. And rather than blowing up in three dimensions, it's going to head off into four dimensions, the fourth dimension. So over here, we still have our three-dimensional looking universe. Why do we say it's three-dimensional? Well, that's because when we view any object in it, like a star or a galaxy, it is only going to exist in three dimensions, a length, width, and height. But this axis here that it moved along is the spatial time dimension. so that when the Big Bang occurred, it flung our galaxy along the spatial-time dimension. And now when we look up into the sky in any direction from this three-dimensional universe, we are in fact looking back along this spatial-time dimension to our one point of the Big Bang. Now, to clarify things, we're going to call this three-dimensional component over here the universe, and the four-dimensional component to be the multiverse. So what we say is that the point of the Big Bang is in the multiverse. Now the multiverse and the universe all is the same. Space is four-dimensional. But we think of our universe as being three dimensions. But the point of the Big Bang is back here in the multiverse. The universe was flung out and expanded in three dimensions, and that is the way it is today. Now, the question that comes up is, what caused this universe to accelerate in that one direction? Well, the answer is quite simple. It's Einstein's mass equivalence relationship, also known as E equals mc squared. Now, originally this formula was used back in the Cold War days to measure the energy of nuclear weapons, because there would be a loss of mass when a nuclear bomb goes off, and you multiply that mass by c squared, and you'll get the amount of energy released by that nuclear weapon. Now, scientists say that that c in this formula is not the speed of light. Now, it has the same value, but it is not the speed of light. E equals mc squared, the c is not the speed of light. Why do they say that? Well, as a mathematician, when I look at that formula, I see an acceleration formula. It says that when energy is converted into matter, that matter is going to be accelerated to the speed c. And according to Einstein, his theory of relativity, in particular the Lorentz factor that he uses, it is felt that matter cannot be accelerated to speed c, that is impossible. And so they consider that c in the mass equivalence relationship just to be a big constant that just happens to match the speed of light. Well, in the theory of time, they are the same value, because the theory of time does not use the Lorentz factor. Therefore, there is no limitation on the speed at which matter can go. And so what happened in the universe is when energy was converted into matter at the time of the Big Bang, that accelerated the matter to speed c along this spatial time dimension. And this universe is going to continue at speed c because, according to Newton's laws of motion, there's nothing out there to slow down our universe. There are no other forces that's going to affect the speed of our universe. All right? Another issue that comes up is when the Big Bang first occurs, scientists say, well, there were equal parts of matter and antimatter that were created. And when this matter and antimatter intermingled, they annihilated each other, but somehow, and they created a process called baryogenesis, although they have absolutely no idea how baryogenesis works, but somehow matter won out, and our universe consists primarily of matter. So somehow equal parts of matter and antimatter became just our universe of matter, that matter won out. Well, that's another one of those things that's hard to believe. They had to create this baryogenesis concept to make this idea work. Well, in the theory of time, we can explain that. There is in particle physics, the standard model of particle physics, there is what we call CPT symmetry. Now the C part is charge, and so that's the creating equal parts of matter and antimatter. The P part is parity, which involves spin, and so the universe, the Big Bang, is going to create equal parts of spinning left and right. Well, one of the things we notice is that things primarily spin to the right in our galaxy. The T part is time. And originally scientists thought time meant you could go forward or backwards into time. Well, we can't go backwards in time. But we can follow two different arrows of time. And so what the theory of time says here is that there wasn't just one universe created at the time of the Big Bang, but there were two. This were the Big Bang. The two universes went out in opposite arrows of time. One universe became the matter universe. The other one became antimatter. The matter universe primarily had a right-hand spin. The antimatter universe primarily had a left-hand spin. And they're both moving in opposite arrows of time. So we're preserving C, P, and T symmetries. And particle physics says that if you preserve all three symmetries, that the physical laws of the two universes would be exactly the same. Now, it would appear that if you looked at the antimatter universe from our universe, it would appear that that universe is going backwards in time. But it's not. Time zero was that point of the Big Bang. And both universes went off in their separate arrows of time, and both are evolving, both are going from order to disorder spontaneously due to entropy. People are born, live out their lives, and die as they move outward from the location of the Big Bang. The only thing that's different is this temporal time, which is moving in two different directions with the two universes. Now, one of the other issues with the current theory is the issue of Einstein's theory of relativity versus the standard model of particle physics. The standard model of particle physics has no problem with these two different arrows of time in the two universes. But Einstein's theory, when you work it backwards, the theory falls apart at the point of the Big Bang. If you go before the creation of matter in the Big Bang, Einstein's theory of relativity falls apart. Why is that? Well, keep in mind that Einstein's theory of relativity added temporal time. That was the difference between Einstein's theory and Isaac Newton's theory, was the addition of time. And this is why Einstein was able to come up with a better formula for gravity, because he added temporal time. Well, what happens when you cross that threshold of where the Big Bang was? You're suddenly entering into a different temporal time. It's like ours, but it's moving in a different direction. And that's why Einstein's formula falls apart. Now, there's probably a corresponding theory of relativity in the antimatter universe, but Einstein is working in our universe with time only going in one direction. And as soon as time flips and is going in a different direction, that's why Einstein's formulas fail. Now, remember that baryogenesis? Well, think about this when you have two universes. When the universes first head out, you've got a universe of matter and a universe of antimatter. So all the matter, for the most part, is over here. The antimatter is over here. They are not meeting each other. So there is no mass annihilation of matter and antimatter. As a result, that's why we can have a universe made mostly of matter and one made of antimatter, even though equal parts of matter and antimatter were created. So now that baryogenesis thing, which made no sense at all, now has a very logical explanation as to why we've got a universe made primarily of matter. All right. Let's talk for a minute about C then. Is C a universal constant? Well, in the theory of time, we're going to say yes, it is. But what it's not is the speed of light. Rather, C is the speed of time. So it's that speed at which our universe was accelerated at the time of the Big Bang. That's the C in E equals mc squared. And if you think about it enough that light is traveling at the same speed c in all the directions, so if it's traveling at speed c in the spatial-time direction, it's also going to be traveling speed c in the length, width, and height directions. And now we've unified c in E equals mc squared with all the other formulas that have c built into them. The c's are the same. It's just rather than light, the speed of light, it's the speed of time. If we want to talk about the concept of space-time, space-time, if you recall, added in a temporal dimension to represent the passage of time. So under the theory of time, space-time would consist of 5 dimensions. It would consist of the 4 spatial dimensions of length, width, height, and spatial time. And it would also have temporal time, which is that arrow of time. So the 2 universes would have different arrows of time, so temporal time will be different between the 2 universes, but the other 4 spatial dimensions would all be the same. Now, concerning the multiverse, the fact that our universe was born as a pair of twins means that you can have this same action occurring in multiple places within the multiverse. You can have multiple bursts of twin universes out there in the multiverse. That's why we call it the multiverse. So our universe now is no longer just this one universe of ours that has galaxies and stuff and is made of matter. But out there in the multiverse can be a multitude of universes. The only thing that we know for sure is that they are divided equal parts matter universes and antimatter universes. Okay, well, as we approach the end of this lecture, let us kind of recap the theory of time then, and how it compares with Einstein's theory of relativity. Both theories agree on the principle of relativity. We looked at that back in lecture 2. We both agree that the principle of relativity governs our universe. In terms of Einstein's other assumption, we differ. Einstein argued that we had a principle of invariant light speed, that as light travels between inertial frames of reference, it's assumed to travel at speed c. Keep in mind, that has never been proven and really can't be proven by direct observation of photons. The theory of time says we have a non-constant light speed. Those photons traveling between different inertial frames of reference could meet up with gravitational forces that will speed up or slow down the photons. So, as a result of this, when we look at redshift, there is a different interpretation of redshift between Einstein's theory and the theory of time. In Einstein's theory, he went along with previous ideas that redshift was a measure of the velocity of a star. Under the theory of time, that redshift now is a measure of entropy. How much usable energy has a photon lost as it's traveled through space? And because we've got 2 different interpretations now of redshift, we've got 2 different interpretations of Hubble's law. Under the theory of relativity, Hubble's law is going to say the farther something is away from us, the faster it is moving away from us. Under the theory of time, the farther something is away from us, the more usable energy it has lost in its travels from that distant spot to the Earth. Both show up as increasing redshift. Both theories agree in the concept of a temporal time. The only thing different is that in the theory of time, we can have multiple arrows of time. And so that translates to multiple temporal times. Now, in terms of dimensions, well, Einstein and pretty much everybody else feels that our universe is in 3 spatial dimensions. But the theory of time adds in that spatial time dimension. And so under the theory of time, we have 4 spatial dimensions: length, width, and height, and the spatial time dimension. That looking out into deep space that unifies distance and time. Both Einstein and the theory of time agree that c is a universal constant. However, we differ on what that constant means. According to Einstein, c is the speed of light, and unfortunately, E equals mc squared, the c in that can't be the speed of light because that violates his principles under the Lorentz factor. But under the theory of time, we've unified those concepts and we have only the one c that represents the same thing in both formulas and represents the speed of time, the speed at which our universe is moving along the spatial time dimension. And finally, rather than just one universe out there, like Einstein believes in his theory of relativity, we have more than one universe. And it's because our universe was born as twins that Einstein's theory of relativity falls apart when we try to go beyond that point at which matter was created in a process called reheating at the time of the Big Bang. It falls apart because suddenly he's in a different arrow of time that's in a different type of temporal time that's moving in a different direction. So, appreciate you listening to these 4 lectures. I know that the theory of time represents something that's just totally different from the current view of the universe. And scientists of today are just not going to accept it because, first of all, they've been indoctrinated in their education into the current idea of Einstein's theory of relativity and particle physics. Okay, and they've got a lot of money invested in their own little research projects that are working on their own little part of that theory of relativity or concept of the universe. However, we hope that young students and future students will look at the theory of time and say, hey, there's ideas in that theory that make a lot more sense than what we are being taught. The concept of the annihilation, baryogenesis, the concept of new space being created out there, and many other things that don't make sense under the current theory that somehow now do make sense under the theory of time. So it is hoped that one day, as these new generations come along of scientists, that they will look at the theory of time and say, maybe there's something to it. Maybe we should give it a look. And just maybe, they'll conclude that the theory of time is a much better theory of the universe than the current theory. We thank you for listening, and we hope you have a wonderful day.